In that case, I suppose we can go on directly to the next talk, which is from Tova, if you're available, Tova.
Yes, absolutely. Give me 1 second and I will share my screen. One sec. Okay. Okay, can you see that okay?
I can.
Yep. All right, fantastic. Okay, so thank you so much for inviting me here today to speak on behalf of the US Muon Collider community. I'll try to give a really broad overview of everything that we're thinking about right now. So let me start with an outline. I'll give you an overview of sort of why muon collider, what's our physics case, how does a muon collider work, and then I'll talk about recent progress, as well as the formation of the US Muon Collider Collaboration, our work with the International Muon Collider Collaboration and the European strategy, and finally some plans and outlook. All right, so let me begin by talking about why muons. So muons are not the particle you would start with when you tried to make an accelerator. I think that's very clear. What you would start with is the much more logical choices of our readily available stable charged particles like electrons and protons. And when you start to question whether or not those are the best particles for your project, are when you start really pushing the bounds of the energy that you're trying to reach. So the question with them is, can they reach the 10 TeV scale and beyond? Tor very much set up a lot of the explanation of what the challenges are here. For those who hadn't heard it already, I'll quickly just go through it. If you try to have a circular E plus E minus collider, your synchrotron radiation can become extremely large because it goes as 1 over m to the 4th, and the electron is extremely light. Which means you have huge power loss, and you can mitigate this with a really giant ring, but even so, it will still be a significant power draw. You could then instead get rid of your synchrotron radiation by going to a linear E plus E minus collider, but then you have something like a single pass, which means that sufficient luminosity requires very high power, and you also have something where in order to get to high energies, you need really high acceleration gradients. So you could, instead of using the electrons, you could go to proton colliders, as we've done with the LHC. And there your constraint is the fact that you are limited in your magnet strength to curve your beam inside of around your ring. And unfortunately, the beam energy is much smaller than the actual energy reach of the collisions because the proton is composite, which means that you really need a giant ring and powerful magnets in order to reach lower energies, effective energies for your collisions. So basically how I would describe the situation we're in is that the use of these particles fundamentally limits our reach. And it may still be possible to use these particles for our next generation of machines, but it's quite hard, as Tor was telling us. But I think most people would agree that to use these particles for the machine after that is almost impossible. So we're sort of starting to reach the limits of our scaling with these particles. And when we had this problem in the past, we overcame it with a paradigm shift. So my favorite example of this is the switch to superconducting magnets when we were working on the Tevatron. And that allowed us to explore new energy. And not only was that a huge success for physics, it was also a huge success for spin-off technology. This launched a huge industry of MRI magnets with the industrial scaling of these superconducting magnets that were used in this process. And I think that this is something that we often point to when, say, advocating on the Hill for our field by saying that this is what it looks like to have government money well spent. I would say we need more paradigm shifts in our field, and we might not need them right now, but we might need them right now, and we definitely need them eventually. And so one option for looking towards the future for potentially our next machine could be the one after that is a muon collider. And this obviously is not a starter beam. You would, like I said, you would never begin by approaching things with muons because muons are not stable, which means that you have to both produce them and that they'll decay in flight very quickly after you do produce them. They have a lifetime of 2 microseconds. However, The fundamental challenge of a muon, which is its lifetime, gets easier with energy because the lifetime increases due to the Lorentz boost. And this has big consequences. If you can keep that beam around longer, it means that your luminosity will increase because you can collide your muons more times. And it also means that the beam decays that you have to deal with in that collider will decrease with energy because there are fewer decays. So basically, as we contemplate higher energies, we reach this inflection point where the muons start to gain an advantage over the comparatively simpler to work with particles like the electron and the proton. Okay, so that's an argument for why you might want to consider muons as you push to higher energies, but you might also wonder why we want the higher energies in the first place. And so I'll make a brief argument for what's interesting about higher energies. And one of those is really deepening our understanding of the Higgs boson. So in the 1960s, we wrote down something that is, more or less a toy theory of how the Higgs boson could look, and we got our wonderful wine bottle potential shape from that. But the reality is that we have never measured this potential at all, and our today's understanding from the LHC looks much more like this diagram in the middle, with these huge error bars around the middle of our of the wine bottle potential and going out towards the edges. All we've really measured, in fact, is this bottom of the potential. And if we want to understand the shape of this potential, what we really need is to explore out of this potential well with our collider. And to do that, you essentially need higher energies to produce multiple Higgs and watch them interact. And so you can't just use a low energy single Higgs factory, as I would put it, but you need a high energy multi-Higgs factory in order to explore this space. And so you can see an example of how these error bars can shrink all the way on the right if you were to explore it with a 10 TeV muon collider. So those error bars are fundamentally interesting, I would say. Encoded in the left-hand side of them is a better understanding of electroweak symmetry breaking and therefore the birth of the universe, possibly. And on the right-hand side is the potential metastability of the universe, the possibility that we could tunnel to a new state in this vacuum. And so I would describe that as the possible death of the universe. So these are intrinsically, I would say, interesting error bars to work down. And then more generally, I'd say that understanding what the Higgs potential is the first step to understanding why it is. And then put in kind of maybe more familiar terms that we tend to use for benchmarking across these machines, if you look at the Higgs coupling measurements that you can make at a muon collider in sort of the redder color in this plot on the left, you can see that they're often beating out, in many cases, they're beating out something like an FCCE precision measurement. Meanwhile, on the right, you have the Higgs self-coupling compared across even more machines. And you can see that even compared to FCCHH, a 10 TeV muon collider wins. So beyond the Higgs, we're also interested in dark matter. So as one really strong example, long favored models of WIMP dark matter are within reach of a muon collider. So I'm specifically talking about the Higgsinos especially, but far out of reach for the thermal masses for what the LHC can do, and also out of reach for direct detection because this sits well below the neutrino fog that these detectors are going to have to be dealing with as they increase in sensitivity. So the Higgs and dark matter give us very concrete targets that a muon collider can find and study or disprove pretty definitively. Meanwhile, we also have this kind of beautiful combination of precision from our lepton collider and energy from this impressive energy reach, which can be combined in EFT frameworks to give us access to higher dimensional operators. And that lets us extend far beyond the center of mass energy in some areas. So here you can see examples of a Z prime search and Higgs compositeness that show that a 10 TeV muon collider can really beat out any other machine that's on the market. Okay, that's sort of the interest in the energy frontier, but with the energy frontier comes a really incredible foray into the intensity frontier. So here in this plot, you can see the unprecedented number of high energy neutrinos that would be produced in well understood collimated beams that could be detected with a pretty modestly sized muon collider detector, a standalone neutrino detector. And so here, there's a real potential for precision high energy cross sections, new DIS measurements, and it could also be possible to strip off neutrinos at an earlier stage of acceleration for low energy beam to study oscillations. I would say that there's definitely much more work needed to further develop the neutrino program, which is not as well developed as the Energy Frontier program. Okay, so that's sort of a background on why we might want a muon collider, and now I will spend some time trying to describe what actually is happening with a muon collider. So here's my really quick overview of a muon collider in my little sketch. The basic idea is that you want to produce, or you want to take a bunch of protons, you want to accelerate them, hit them on a target, produce pions, which then decay to muons that have huge phase space flying all over the place. You want to wrangle those muons. You want to accelerate them as fast as you can, and then you want to put them in a collider ring and focus them as well as you can in your detector. The overarching driver for all of this design is the luminosity that you can achieve. So basically, you want to create as many muons as you can and then cool and collide them as fast as possible, because as soon as they exist, time is working against you. And here on the plot on the left, you can see how a beam decay rate looks as you're ramping up in energy. So you start out at low energies, having a really fast loss of the beam, but as you reach higher energies in that acceleration process, this sort of starts to steady, and you can keep your beam around for longer. Okay, so focusing in on the different steps here, I want to talk a little bit about what's interesting, challenging, and things we're working on for each of them. So for the proton driver, what we want is a high power proton driver, 2 to 4 megawatts, and this gives us our starting constraint on the number of muons we can produce. We'd like to have them at 5 to 15 GeV, and this is basically a range that's optimized in order to create as many muons as you can from the protons. And you want a 2 to 4 nanosecond bunch size, which is small, in order to reduce that initial emittance of the muon cloud that you're creating, because this is the one area where you can actually get that down before you start cooling. In order to get all of those muons into one tiny space, your space charge is a key constraint. So basically, this can push your beam to higher energies in order to increase the bunch density. I would compare this to spallation sources. This is a pretty similar operation, just scaled up a little bit with smaller bunch sizes to what we're doing at places like the SNS. Okay, so then we want to take this proton beam and slam it into a target, make those pions, and capture the resulting muons. So we have to have that target deal with all of that power from the proton beam, again, to make sure we have a good starting number of muons. But then we have to also capture everything that comes off, which requires a pretty impressive single magnet. Our current parameters say a 20 Tesla solenoid with a 0.7 meter radius, and this is something that you could kind of compare. It's not the same, but it's sort of similar complexity to what's being done at fusion facilities. And so basically, the higher the field, the more pions and muons you get, but you need this large bore to accommodate the shielding so that this magnet isn't suffering from the radiation from what's coming off of the target. So these are really pushing the limits of what can be done today, but it is all very synergistic with the fusion facilities, also neutrino beams and spallation sources. After that, we have our cooling channel, and this is using the concept of ionization cooling. So this is basically the idea that you would put a beam of particles with lots of different momenta through some material. They'll lose momentum via ionization, and then you accelerate them all in the same direction at the same time. And what comes out is a beam that is more aligned than it was when it started. So the physics concept is pretty simple. It's really the engineering that's a challenge here. So you need to cool the beam by 6 orders of magnitude in its total phase space. And there's, 6 parameters of this phase space. So you can kind of think of this as something like an order of magnitude in each one, although it doesn't exactly pan out that way, but to give you a feeling for sort of how much we're physically shrinking the beam by. And that's in order to get the high luminosity that you want from having good beam focus inside of the detector. You want this channel to be as compact as possible to reduce the loss of muons due to decays before you really get the chance to accelerate it. And as you go down this channel, you start to get more challenging to build cells. And in particular, by the end of it, you need peak B fields up to 40 Tesla, albeit with much smaller bores than what we were just talking about. And this gives really strong focus and improves the final cooling rate. So this is something that's quite novel for a muon collider. There's really nothing else to compare it to here. but many of these principles have been demonstrated throughout the years. Okay, up next, we have our rapid acceleration. You need average gradients up to 2.4 megavolts per meter, and you need fast ramping magnets in order to keep them in this ring as they're changing energy so fast. And so this is needed in order, again, to increase the muon energy before the muons decay. So the high gradients you can compare to linear colliders, but the ramp speed is a pretty unique need for a muon collider. And one way that we get around some of the difficulty of that challenge is by using a combination of fixed field and ramping magnets, so that you can use the full range negative to positive on the ramping magnets on top of a fixed field. Okay, then once you get to the collider ring, we're trying to shrink this collider ring as small as we possibly can so we can collide the muons as many times as we can before they decay, again, to increase the luminosity. So you need dipoles, ideally at 16 Tesla, although there's some flexibility on this depending on what your target is. You need integrated design of the machine detector interface because you really need to both optimize focus for that luminosity and minimize the beam-induced background that's going to be flying into your detector. And you also need some kind of strategy for mitigating the neutrino radiation around the ring, which in the IMCC designs involve both modulation of that beam as well as mechanically moving the setup on the scale of a couple times a day. So this requires a lot of engineering and scalability of HTS magnets if you do want to hit the 16 Tesla dipole, and that's the biggest constraint. But there are energy staging options that are using niobium 310 to make it achievable with less R&D. So you can compare the dipole needs to FCCHH, although there is a scaling option, but the neutrino mitigation is pretty unique here. Okay, finally, we get to the detector. And here we have a detector that has to be able to deal with all of these beam-induced backgrounds. One way you do that is by keeping the occupancy down, by just creating extremely small feature sizes and also having precision timing so that you can cut out beam-induced background arriving out of time. You also want a 5 Tesla solenoid, which is primarily in order to reduce the incoherent E plus E minus backgrounds that would hit your first layer of your detector, but also conveniently gives you very good high PT precision for the signal that's going to come out. And the detector, it has a lot of similar components to what we're building for the HLHC and the CMS and Atlas detectors, but the biggest change is integrating timing into all of these layers. So the challenge is maintaining reasonable power and readout while you're adding all these things together. Okay, so like I said, the cooling channel is one of the most unique to a muon collider, and therefore that's what's really the main focus of this concept of a muon collider demonstrator that you've probably heard about a few times by now. So the major concept, like I said, is ionization, and we know that DEDX works, right? There's no question on the principle of physics there, but the real question is, can we engineer a system that can really take advantage of it? So we want to be able to engineer the cells that are involved, construct them, operate them in a chain, including with beam going through them so we can see if there's any breakdown. So there's multiple options on the Fermilab site to both study muon production and capture and cooling there, as well as cavity and performance with higher intensity proton beams that could tell us about how the cavity interacts with beam. So there's a new Fermilab LDRD to develop a detailed design, and we hope that this will go forward. Okay, so that brings me to thinking about this in the context of Fermilab more generally. So here you can see the plan for the proton complex at Fermilab, and there's a series of upgrades that are involved. So we start out with our existing megawatt proton beam. Then the PIP2 includes a LINAC upgrade that increases the injection energy and booster cycle rates increased. Then ACE MERT works on the main injector reliability as well as its cycle time. And then finally, there's a booster replacement, which we would really need to have components that are compatible with what we would need for a muon collider. So this requires a lot of working together with the folks involved in this to make sure that we're sort of working towards the same future. So I would say that the future of the U.S. Muon Collider effort is integrated in this way with the future of Fermilab. As was mentioned earlier by Paul, the U.S. Muon Collider coordination team just had a really nice meeting with the Fermilab director search to discuss priorities. Okay, so let me try and put some of this work into a timeline to give you kind of a sense of a non-exhaustive recent history of Muon Collider work. So here in blue, I'm trying to highlight some of the major things that have happened either in the Muon Collider community or outside of it that have made it look like it was more feasible now to start working on a Muon Collider. So early on, you have cooling design that's in the 2015 or so that looks really like it could work. Then you have places like the SNS achieving really steady operations with a high power proton beam. You have ITER central solenoid modules being completed, which are sort of similar in complexity to what we would need. Then you also have things like the Atlas and CMS HLHC upgrades, having their TDRs finalized, or building technology that's kind of a step away from what we need in the detector. So as we're having all of these advancements in our technology, we're also seeing increasing excitement in the US community towards a Muon Collider, first in SNOMAS, and then the strong recommendation from P5, and then I would say even the stronger recommendation from the NAS elementary particle physics report that put US Muon Collider as its top recommendation. And meanwhile, the US community and the international community have been organizing. So right before SNOMAS, there was the formation of the IMCC, the International Muon Collider Collaboration. And then just this year, we formed the US Muon Collider Collaboration. Okay, so, excuse me. I want to talk about a couple of recent highlights that have happened in the last year, less than a year, last handful of months. And talk about some things that are making steady progress in Muon Collider R&D. So here's two pieces of work that are pushing the compactness of the accelerator design. So the one on the left is looking at RCS design, so how we can get acceleration on the Fermilab site. And what we can see here is that we can keep through these variable designs at least 65% of the beam, which is really fantastic. And we also can see that we are close to targets, but not yet within targets for what we can do on the Fermilab site. So what you can see here is a series of rings. There are a lot of different strategies being explored, but I want to highlight two. There is one that is only using that's only using rings that can fit within the Fermilab site, and there the highest energy you can get to is 5.42 TeV. Meanwhile, if you go a little bit bigger than the Fermilab site, the maximum ring size you need is 21.9 kilometers, and you can get to 10 TeV that way. But this is all using no HTS magnets, only niobium 310, and is a work in progress for optimization, so we could well do better through optimization as well. Okay, on the right-hand side, we have some cooling channel studies that are studying a unique design that lets you cool both muon, charged muons and the positive charge and negative charge in the same channel together, which is sort of impossible in a typical one. And so this is something that could make our cooling channel more compact and reduce its cost by doing so. So you can see both of these are making nice progress. And meanwhile, I wanted to highlight both of those because those are both works that were done within some really wonderful groups. We have training new students in clusters of new students at once in Muon Collider Accelerator R&D. So for example, we had 6 students based at Fermilab for the summer, which you can see on the right-hand side here. And we have 4 students that have already been incorporated into the Brookhaven LDRD. And we're interested in expanding these kinds of summer programs and other programs in future years, which needs funding both for the students and for expert time. But you can see the fantastic results that are coming out of it. So on the right are summer students at Fermilab. And basically what I want to say here is that it's really clear that Muon Collider is an excellent motivator, attracting a new generation to accelerator physics. And we will have a training week next week, actually, Muon Collider Accelerator School, that will be training even more students in the basics of accelerator physics in the context of a muon collider. Okay, and just to put even finer a point on this, I was just at a talk this week that was discussing the high luminosity LHC project. And for a much, much smaller scale project, this is their FTE that's required as they're really getting to the most intense parts of that project. And I think these numbers really demonstrate just how much growth is needed in accelerator physics in order to enable a large scale US collider. Okay, moving on to the detector concepts. This year, roughly, 2 detector concepts were developed for 10 TeV, and one of them, Maya, is led by the US and DAISY. And we've been working very closely with the machine detector interface designers to assess and mitigate the beam-induced background, which you can see pictured here. And we've been moving from relatively simple to much more complex object ID and quantifying performance. So in this link on the top left under the Maya logo, you can see some comparisons between signal and bib, but here I'm focusing more on the algorithms themselves. So you can see the improvement, so you can see how we're increasing in complexity. So we're going from, say, photons, which is a single detector object, to a charged pion, which starts looking at combinations between the tracks and calorimeter. And finally, we begun this month looking at the 5 TeV hadronic decays of extremely boosted bosons and trying to understand if we can pick these apart and differentiate them from one another. Okay, one other thing that has sort of recently come more into the attention of the folks working on detectors is the interesting hierarchy of rates at play on muon collider. So we have a 1,000 times lower bunch crossing rate than the LHC, but even after that, there's 4 orders of magnitude between that crossing rate and a lot of our key processes like boson production. And in between that is sort of interesting stuff that we have to decide if we want to read it out or do we want to develop a trigger that can work for these. And one question that comes into mind there is, are some of these valuable for luminosity? They should be, a lot of them are correlated with the luminosity, so it may be possible to use them for that. And also there's other interesting features like the neutrino interactions with the detector actually happen at a really high rate compared to a lot of other processes. And so we have to decide, is this a nuisance? Is it something we can use for physics? How do we want to handle this? And all of this is sort of this really unique hierarchy of rates really has a lot of implications for how you would design your detector readout, which to date, we've mostly been trying to think about as a streaming readout, but we want to understand this further. Okay, so moving on to the USMCC. I won't read all of the text on this, but this was formed this year, and our annual meeting is next week. The core purposes are to define the necessary work for a mid-P5 panel, to design a US demonstrator, engage with the international community, create a long-term vision for Fermilab that leads to a muon collider, and build on a theory-driven physics case. We ratified our charter in May, and we elected our first leadership last week, and we are now in runoffs for one of the positions. We currently have 244 members, and if you're interested in joining, you should absolutely reach out to us. You can email us if you're interested. And when I say us, no, sorry. Well, this is who the members are. So just to give you an idea of the members, we have a healthy number of faculty and lab scientists, but also some graduate students and postdocs. And then looking at the areas, it's about half experiment, but you'll notice there's also a green slice that says experimental at the top. And that 4% is actually people who list both experiment and accelerator, which is, I think, a very nice thing to see. Okay, so coming back to who you should talk to if you're interested in, this is our newly elected leadership. So Sergo Dendariani is our new chair. I am the vice chair. Our communications chair is currently in runoff, and we have 2 excellent candidates that are in that runoff, Larry Lee and Kylie Kennedy. So we'll find out, I think, tomorrow which one of them wins. And then we have representatives from each of the frontiers. Accelerator Experiment and Theory are Dictus, Monet, and Patrick. And we'll soon also begin naming members of a broader leadership strategy group that will have a lot more representation across the field. Okay, coming to the IMCC, there was a recent IMCC annual meeting in May, and the US was very involved. In fact, Kylie, one of our Competitors for Communications there was one of the co-chairs. And there were many other meeting organizers, presenters from the US. About 20% of the participants were from the US. And we are very interested in maintaining close relationship with the IMC. I think it's very clear that an ambitious program like this one requires a global effort. So I've only shown a few highlights here, but if you're interested in all of the progress, you can click through to this annual meeting and see the 181 contributions across all of these areas. There was also a training day there, and there's a lot of enthusiasm in the IMCC for an increased US role. And we have a US CERN Muon Collider MOU that's in progress and making its way through the DOE. Okay, one of the main successes, I would say, of the IMCC in the last year was putting together this truly impressive document, 400 pages, on the status of the Muon Collider effort, which I've taken a lot of items from throughout this talk. It's a great resource if you're interested in understanding almost anything more about the effort we are working on. And that core editorial team involved a whole lot of US members, but we also had an additional US supplement that was 12 pages detailing our regional plans about how we see the US effort. Okay, so all of this brings me to the sort of most recent event in the US, which was the NAS EPP report, which was released June 11th. And this had as its first recommendation, the United States should host the world's highest energy elementary particle collider around the middle of the century. This requires the immediate creation of a national muon collider research and development program to enable the construction of a demonstrator of the key new technologies and their integration. So I would say that this reinforces and adds more urgency to what we had already heard from P5 in 2023, and really lets us know that we should continue pushing on this challenging effort. So thinking about how we actually approach facing all of these challenges that are associated with the Muon Collider R&D, I wanted to give an overview of what US Muon Collider funding looks like right now. So at the labs, this has mostly been driven by LDRDs. So at Fermilab, there are two of them that are relevant for the Muon Collider. There's one that's focused on demonstrator design that I mentioned earlier, and there's also one on future collider software. Then at Brookhaven, there's an LDRD focused on RCS and cooling cells. At Berkeley, there's a future collider detector LDRD that has a Muon Collider component. And SLAC actually has DOE GUARD funding for a high field RF test stand that's extremely relevant to the cooling channel of a Muon Collider. Meanwhile, at the universities, a lot of the dedicated funding for Muon Colliders has come from private foundations. So there's a sort of joint accelerator and experiment Simons Foundation grant, as well as several fellowships, so early career kinds of fellowships like Sloan and Cottrell. And then we have a Kavli Foundation supported interdisciplinary seminar series coming up that will begin in the fall, as well as startups from many of our early career members, internal funding, fractions of base grants, and early career awards. So there is funding in the US, but it's sort of scrappy, small scale funding that we've been piecing together to sort of power the progress we've made so far. But I would say when we're talking about ramping up our efforts, we're still constrained by a lack of significant R&D funding from the government agencies. Okay, so with all of that in mind, this is my major takeaways from the US Muon Collider community. I would say the reports are in. Muon colliders hold huge potential for the US and for the future of particle physics across a lot of different areas. And the US community is engaged and very eager to ramp up, but we still have big challenges to solve. We are writing more papers every year as we're solving more of those challenges, but we need more people and more resources to actually make it happen. And we also are very interested in having more people join. So if you're interested in getting involved, you can click on this link to go to our website, muoncollider.us. You can also self-subscribe to our mailing list, or if you'd like to actually join the collaboration, you can email me or Sergo. Okay, thank you.
Okay, so thank you very much for this well, I guess exciting discussion of the current state and also really clear discussion of the future for the Muon Collider ideas. We have several questions here. So the first is from Sanjay Sood, who just asks a very general question: is how strong is the case for building the muon collider at Fermilab?
Yeah, it's a great question. I hope I've at least largely answered it with the talk. I think the physics case for a muon collider, wherever it is excellent. And there's a lot of really great synergies for its placement at Fermilab. We have already the proton complex, the experience with muon beams, and we've already done ionization cooling in the context of those muon beams. So there's a lot of expertise that we can take advantage of and a lot of facilities we can take advantage of. The big constraints are fitting the rings on site, and we can decide if that is an ultimate constraint or not as we work on these designs and go further. But I think it's a really promising place to host this collider.
Okay, the second question is from Brendan Bullard at Slack, which is, has the muon collider community identified any technological spin-offs and industry synergies can benefit from the realization of a multi-TeV muon collider? And I might add, these are questions you got ahead of time, so they may have been partially answered already.
Yeah. I've tried to brush, sort of touch on a little bit of these. I think one thing I wanted to say, I saw this really wonderful talk from Luca earlier this month that was talking about the industry created by MRIs, which I mentioned earlier. This will sort of continue as we've had MRIs, we've started making more and more complex MRIs, fMRIs, things that want to take in a lot of data and want to be able to do it quickly. And stronger magnets make that possible. So as we continue to push magnet R&D, especially when we're talking about high field solenoids, this is something that will continue to help this industry. And this is now a $7.3 billion industry that was sort of launched, like I said, by the creation of the Tevatron. So this is something we can continue to work with. But I would say more generally than that, I think this is something, or more specifically to muon colliders, this is something that we're continuing to work on. There's a lot of ideas around things like non-proliferation. There's a lot of interest from other frontiers in our neutrino beams. And there's, a lot of different technologies being explored here, but I think we need to do more work to actually have a bunch of clear messages about potential synergies.
Okay, thank you. And next question is from a certain John Beggar from Johns Hopkins and APS. And he says, I am willing to stipulate that sooner or later the muon collider's technical issues will be solved, but he wants to ask about radiation mitigation, not just to the surrounding environment, but just as importantly to the groundwater. What is the plan? And thank you.
Yeah, fantastic. I learned a bit about. I already knew some things about this, but not a lot of detail because the nice thing is that this has been looked at with a lot of complexity, sort of beyond my understanding via the CERN people who are really experienced in understanding all of this radiation mitigation from, for example, having done LEP. So the main idea with a muon collider is that you have a whole lot of different neutrino beams that can come off of the detector, and these can travel quite some distance before they interact. So you have to worry about kind of longer distance scales for radiation compared to what you would normally have without neutrinos. Coming off of the straight sections that surround a detector is the most intense neutrino beam, but that's exactly where we sort of want it. So there's a couple of these regions that are coming off of the detectors, at most 4. And those are places where you might want to build a neutrino facility and have it be radiation controlled. So this is sort of part of the plan to very carefully control these areas. Coming around the beam from the smaller straight sections around, and even just the round sections, are lower intensity, but also really important sections. And so it's really about making sure that those regions are safe for the environment around. And so the IMCC has worked on a couple of different strategies of smearing out those beams. So they're basically trying to make some kind of changing of the pointing of the beams around the ring with time, so that instead of having a pencil-like radiation profile like this one here, you have something that gets smeared out. So no area is nearly as high in terms of dosage. And so that's been done both with kind of just moving the beam within the magnets, and also moving the whole physical system. They're designs for both of those. The actual details of the activation have been studied in detail from the CERN folks who study this and who are professionals at this. And they have definitely done a lot of work. I just screen capped a slide that you can find more details at this link that's actually looking at the distance from the collider to where there would be groundwater. But the good news is that there's a whole lot of material at CERN that isn't groundwater that you have to go through before you get there. And so they're able to do projections based on that. But I will say at the Fermilab site, we haven't been able to do any of these detailed projections yet. And this is very much something that we need to basically get funding in order to work on.
Okay, thank you. And let's see, the next question is from Alexei Petrov at USC. And this is one that came in today, is how closely do you work with the intensity frontier muon community? Does the development of low energy muon experiments at Fermilab, such as the Advanced Muon Facility, help the case for the muon collider?
Yeah, fantastic. It is absolutely the experience of the folks who are coming from that campus that is helping move forward the US effort from the accelerator side. So for example, this Fermilab LDRD that's trying to make a demonstrator design is led by Dictus, who works on mu to E. And so we really want to take advantage of that expertise. I think the challenge is getting those folks time and paying for it with funding, because they have their own jobs to do, and we would love to take some of their time, but we need more workforce and more money in order to really take advantage of it.
Okay, and I think we have three more questions. One's from Kevin Black, and I have an add-on to that one. It's
Okay.
Kevin's question is, many of the magnet challenges that exist for the muon collider are also important for fusion research and a lesser extent MRI machines. I don't know, and I actually was going to ask what kind of R&D is needed for a 40 Tesla magnet, which seems to be part of the cooling channel. So could you just comment on the magnet R&D in general?
Yeah, absolutely. So the high field magnet facility in Florida has been making magnets at this scale. The main thing that you need to do is to have a very small bore for these. So the idea is to only use these at the very end of a cooling channel where your beam is compressed enough that you don't need a huge bore for that, plus the shielding from it flying all over the place. So this is only something you would consider doing at the very end of that cooling channel. It's still a challenging magnet to make, but it's not as crazy as it sounds if you're used to high bore magnets.
Yeah, so just maybe synergies with fusion research and MRI.
Sure. Yeah. So the fusion research, I mentioned the ITER solenoid. The ITER solenoid is lower field. It's I think 12 or 13 Tesla, but higher bore size compared to our capture magnet, in a way that in complexity very, very roughly balances out. So it's sort of an equally challenging, similar kind of magnet. So definitely that experience will be really useful. The US experience of constructing that magnet will be really useful if we take that design and want to put it around our target. And then for MRIs, yeah, the main thing there is having high field superconducting magnets with bores large enough to put people in them. And that's very connected to things like our, very connected to the magnet design that goes throughout that cooling channel.
Okay, our last question that I can see, unless there may be some in the chat. Okay, let's see. Yeah, I'm just looking at is from Robert Ryan, and it's the new storm facility was proposed in 2013. At that time, P5 did not embrace it due to the focus on other priorities. However, New Storm is arguably the first step in a long road to a muon collider. Given the growing worldwide interest in a muon collider and given the recent NIS report, is Fermilab considering the possibility of building New Storm in the future? And maybe that's
yeah, I don't want to speak for Fermilab. I think from the muon collider side, we really want to spend more time refining the kinds of neutrino beams that we can build as we progress from the demonstrator through to different cooling stages and acceleration stages, and finally around the collider, the ones that I have up on this slide. We want to characterize these really clearly so we can work with neutrino theorists in order to understand the physics potential for each of these beams, and work that into our plan.
Okay.
Someone from Fermilab wants to speak up about the plan they're walking
Yeah,
through.
maybe anybody from Fermilab, but otherwise, we're
We could leave
actually,
that to the end of the meeting also, if we have a general discussion time, and give the Fermilab people or the agencies an opportunity to consider it.
okay. Otherwise, I don't think I see any more questions. And let's see. Let's go on to, I will hand off to Sally and